So hello everyone. Welcome back to Vector101. Today we'll be covering kind of the topic that you've all been waiting for, in a sense. The topic that was, I think, most promised in the course description, which is affine transformations. Now, everyone here who has ever worked with Roblox has worked with affine transformations before, through C-frames. As Ethan mentioned last week, C-frames are examples of so-called affine transformations. But I am a mathematician, and so my goal is to explain first what an affine transformation even is before we get into specific types of affine transformations. So what is an affine transformation? Well, we talked a little bit about linear transformations. And by a little bit, I mean most of the course. So can anyone recall what the definition of a linear transformation is? Like the definition that I gave way back when we introduced them. Yes, it's a function that distributes over linear combinations. So what would you expect an affine transformation to be? It's happening again, people. I'm getting the moving. At least one guess in the chat before I reveal what an affine transformation is. Oh, so Borb thinks it's going to be very different. The answer, in fact, is that an affine transformation... Oh, there we go. Borb was lying to me. I feel tricked. An affine transformation is, in fact, a transformation that distributes over affine combinations. Now, I am going to level with you. Until preparing for this lecture, I had not realized that. I basically, by the time I learned about affine transformations, this kind of going back to like the very simple definition was not really something we did. We basically just were like, well, linear transformations, they're linear transformations plus b, and that's how I learned them. But it does turn out that that affine transformations are defined as functions that distribute over affine combinations. And this is I think a really interesting idea, or a really interesting thing to note, because I think oftentimes when affine transformations are presented, they're just written like this. And so we want to get to this formula, right? So what I mean by this formula is that if I have some affine transformation, just any affine transformation, we can always write it as some matrix times our input plus some constant vector. And I want to work towards that in a very similar way to how we worked towards linear transformations. Let's do that a little bit. I'm going to go kind of faster than we did the first time we talked about this kind of stuff, because you all should at this point be familiar with some linear transformation stuff, right? So let's just assume that we have this transformation T, and it distributes over affine combinations. So we will assume this set of conditions, right? So to kind of review, an affine combination is just a linear combination where all of the weights, all of the alphas, they all sum to 1, right? And that's an affine combination. So the first thing to realize is because affine combinations are linear combinations, if we have some linear function A, then this, and we have some affine combination here. Now, I'm not going to write out that this is an affine combination, but it is an affine combination. Then this is going to distribute, right? Because linear combinations distribute over all linear transformations. So, in particular, right, linear transformations are affine transformations. Are there any questions about why linear transformations are affine transformations? People are typing, so I'm going to wait just a bit more. Yeah, so yes, an affine, well, so actually, Borb, you bring up an interesting point. So Borb said affine transformations are just constrained linear combinations. But this actually isn't true. In fact, the opposite is true. And I want to, it's probably good to talk about why, right? So, right, a linear transformation distributes over any linear combination. Why does this thing hate me? Any linear combination, right? So that's a quite large set of combinations, right? That's any scale, that's any sum of scalar multiples of vectors this has to distribute over, right? And so this is a large set of things, right? However, a subset of linear combinations is affine combinations, right? And you can think about the fact that I have to distribute over linear combinations as being a number of constraints that we put on our thank you. This is a contains in. So this is the same. This is a sub. This bottom thing is a subset of this top thing. But what I'm saying is basically there are fewer affine combinations than there are linear combinations. And so you can think about having to distribute over linear combinations as being a number of constraints, right? We're constraining what our function can be. And remember, not remember, and think about it. The more I constrain something, the fewer options it has, right? If I have this circle, if you imagine this circle being the set of constraints, right? So we only can be inside the circle. If I constrain it more, we have fewer options, right? And so actually, what going from linear combinations to affine combinations is doing is, well, the inside here, the more constrained part, that's linear combinations, because we're constraining it more. And then actually, we're constraining it less when we allow affine combinations, right? Because again, more constraints, fewer constraints. So more constrained on the inside and less constrained on the outside. So there are actually more affine transformations than linear transformations. And so basically affine, just from this analysis, right, just from the way we're thinking, yeah, so I guess just to be clear, because to clarify, yes, affine combinations are more constrained. There are fewer affine combinations, but how to explain this? Um, let's say that we have let's say we have here. You know, omnivores and carnivores, right? Omnivores can eat, assuming they can eat anything, and carnivores can only eat meat, right? So now let's relax that a bit. Instead, let's just say a carnivore is no. Let's say a carnivore is anything that can eat meat. Uh, uh, no, omnivore and carnivore. That's fine, right? So, like it, the omnivore has more things it can eat. Is basically like the linear transformation, right? So there's more options for the omnivore, and affine combinations are kind of the carnivore. They no, this is not working. My analogy skills have failed me. No, I guess this works. Yeah. So trying to get this right. So yeah, I guess you can think of it like, well, yeah, no, I think this analogy works better, where it's like, uh, if you stop thinking about the constraints on the combinations and start thinking about the types of combinations as constraints, right? Then again, there's fewer affine combinations, which means there's fewer constraints on the functions. There's more linear combinations, which means there's more constraints on the functions, right? And so basically it switches the directions. But that's a little bit too long on that particular topic. But yeah, I guess the one thing I'll draw another one of these pictures here, which is like, you can think about, like, again, I start with like the set of all possible functions, right? It's this big unbounded, unconstrained set, right? Then if I say, well, I have to distribute over affine functions, or sorry, affine combinations, that's like maybe this set of constraints, right? So now I'm allowed to be anywhere inside of this, right? But every affine combination is a linear combination. So if I say that you have to be constrained, that if I say that you must distribute over all linear combinations, right? Well, then that circle of functions that distribute over linear combinations must be inside this circle, because everything in here must also distribute over affine combinations, right? And they must distribute over non-affine combinations. I hope that makes sense. I think it's a very important point to make, which is why I'm willing to spend quite a bit of time trying to make the point. Because this kind of idea pops up in math all the time, where like you have one thing where you have a bigger set and then a smaller set, and if you look at the functions on those sets, the order gets reversed. The functions corresponding to the bigger set are smaller, and the functions corresponding to the smaller set are bigger. And so that's basically what's going on here. But just from this kind of argument, right, what we can assume is that if I have an affine transformation T, and we're applying it to X, then this affine transformation, it's going to have some linear part, some part of it that's linear, right? Because every linear transformation is an affine transformation. And then it might have a part that's not linear. And I'm going to call this little t of x, right? So you have a linear part, and we have a nonlinear part. And we're going to try and kind of figure out what we think this nonlinear part might be. So let's think about it briefly, right? We basically want well, actually, let's think of an example of an affine transformation first. I'll talk about an example. So what's an example of an affine transformation that isn't linear? Well, actually, a good one is if I just take the t of x equals x plus 1. Right? So the reason this isn't linear is because if I take t of x plus y, and these are real numbers here, I guess. If I take t of x plus y, this is going to equal x plus y plus 1, right? And we want this to equal t of x plus t of y if we want this to be linear. But that's x plus 1 plus y plus 1, which is x plus y plus 2, right? And so these two are not equal. Those are not equal. So this is not linear. But what if we had t of 1/2 x plus 1/2 y, right? Well, this is going to equal 1/2 x plus 1/2 y plus 1. And that's equal to 1/2 x plus 1 plus 1/2 y plus 1. And this equals t of x plus t of y, right? So despite this, and this isn't a proof, but like this here was a linear combination that wasn't affine, and it didn't distribute. But this was an affine combination, and it did distribute, right? So I haven't proved to you that it's affine, but I will make the claim that it's affine, right? And so what does that mean? Oh, I did lose some 1/2. Thank you. You're so correct. But it's hard to get them back because my thing hates me. Yeah, these are 1/2. Right, so this does distribute, and the way to think about it is, right, like we talked about affine spaces. Affine spaces are a linear space plus a shift, and this x plus 1 is a linear transformation plus a shift, plus 1. So this is affine. Now, again, let's go back to this form here, right? Well, if we go back to this test here, right, where we just like plug in 1/2 x plus 1/2 y, that's a pretty good affine combination to work with for testing purposes, at least. And if we assume that t of x equals ax, so this is some matrix times x, plus t of x. This is just some function of x. Well, again, if we do t of x, we do t of 1/2 x plus 1/2 y, right? This is going to be equal to, if I work it out, it's going to be 1/2 ax plus 1/2 ay, because the linear part distributes, plus t of 1/2 x plus 1/2 y. And if I assumed this distributed, right? If I wanted to know what 1/2 t of x plus 1/2 t of x would look like, or t of y would look like, then this would be equal to 1/2 ax plus t of x plus 1/2 ay plus t of y, right? And so the only different parts of these equations are this t of x here and this t of y here as compared to this, right? So really what we're saying is, in order for this function t to be affine, right, we need this to be equal to this. That's the definition of being affine, at least in this case. Or we want this. Okay, so if we set these two right-hand sides equal to each other, this is identical to saying that we want t, I forgot the 1/2 again. We want 1/2 t of x plus 1/2 t of y to equal t of 1/2 x plus 1/2 y. Right. And importantly, we're not going to allow t to be linear. So this has to be achieved without t being linear. And I claim that at least the most obvious answer is to assume that t of x is just some constant vector b. Now, what's the intuition here? Well, suppose that we had an entirely different combination. Let's say we had x0 plus 1/2 y0, right? That also equaled 1/2 x plus 1/2 y, right? Suppose we had this. Well, then this right-hand side would be the same if we evaluated t at this x0 plus y0. The right-hand side would have to be the same, which would mean that basically that this equation must then hold, right? And so in particular, like t of x0 and t of y0, when added together, must be the same as t of x plus and t of y, right? These must be the same value. And if you kind of work out the math, it turns out that the only function that will do the trick here is going to be assuming that this function actually just constantly outputs b. And that will be a homework problem to show that. But I hope that kind of makes sense a little bit, right? Like we start with just assuming that this affine function is a linear part plus a nonlinear part. And then when you like go down, when you do the work, you find that like, oh, this nonlinear part essentially has to behave almost linearly. And if you then do the homework, you'll find out that the only option for that function is to assume it's just constant. So are there any questions about that? I think it'll make more sense when you do the homework because there'll be some steps in there. But I just wanted to kind of like go over the kind of steps for why one might assume this general formula, which I am again going to write. One thing to point out is if we have alpha 1b plus alpha 2b plus ... plus alpha k. It does not like me. Plus alpha k b such that all of these are 1. Oh, sorry, no. All these sum to 1. This is just going to be equal to b. Right? Because 1/2 b plus 1/2 b is just going to be b. So that's kind of another way of thinking about it. If you take an affine combination of the same vector, you'll get back that vector. Whereas if you take a linear combination of a vector over and over again, you could get a scalar multiple of the vector. Are there any questions so far? Okay. So even if you didn't get that whole discussion we just did, which would be fine because you'll go over it again in homework, the point I want to hammer across really is that every affine transformation, every transformation that distributes over affine combinations, can be written as a linear part plus a shift. And this is all possible affine transformations. So now that we know that, we don't have to redo a lot of work, right? So what I now want to do is I now want to define what it means to add two affine transformations and what it means to multiply two affine transformations. But we already know how to do these things for matrices. So it's actually very quick to figure out how to do this. So if we have, I'm going to add a 1 and a 1 here. If we have T and S both being affine transformations, how do we add them and how do we multiply them? Well, first of all, for now, let's just assume that A1 times A2 makes sense, right? Because if you remember, matrix multiplication only works if these matrices are in, n times m and m by k, right? So let's just assume that that's working. And actually, let's even assume something stronger. Let's assume that both of these matrices are square. So these are actually going to be an m n by n. And that'll just make the discussion a little bit easier. You can redo the discussion, but it's just easier to assume that all multiplications make sense and work out and everything's great. So what do we want t plus s of x to be? So what we want it to be is we want this to be equal to t of x plus s of x. Okay, that's easy, right? We just plug in our formula. We get that this is equal to a1x plus b1 plus a2x plus b2. And this is equal to a1 plus a2 x plus b1 plus b2, right? So we just add the linear part, we add the constant part, and that gives us our new affine transformation. Great. So what if we want to multiply? Well, we want t times s of x to be equal to t of s of x. Well, again, okay, we can just plug it in. We get a1 times a2 of x plus b2 plus b1. So we can distribute this out. And it turns out that this is going to be equal to a1 times a2 times x plus a1 times b2 plus b1. This dot's just multiply, not a composition dot. We're defining what it means to multiply to affine transformations. And now, yes, we want multiplication to be the same as composition, but we are genuinely defining a notion of multiplication. And I want to point out something here. This part here is just, this little part at the end, is t applied to b2, right? Because we have a1 times b2 plus b1, right? And that's exactly the definition of t applied to b2. So really all we've done is we've multiplied the linear parts, and then we've applied t to the constant part. And like, this is perhaps the most interesting thing about affine transformations, which is multiplication. Because this has a really interesting consequence that you're actually all familiar with from working with Roblox, but it's kind of interesting to see it from a math perspective, I think. So let's think of an example of an affine transformation that's not quite as boring. Well, what can a linear transformation do, right? Because affine transformations are just linear transformations plus a shift. So linear transformations, they can rotate things, they can scale things, they can shear things, which I don't know if you've said that explicitly, like what that means explicitly. But we're going to be interested here in rotation. So let's say that I want to take a point. I want to move it down. So we're going to be in 2 dimensions. Sorry. So I have a point in 2D. I want to take this point in 2D. I want to move it down 1 unit, and then I want to rotate it by 90 degrees to the right. So 90 degrees clockwise, right? So if I was in 2D and I had a point here, I would want to move it down 1 unit, and then I want to rotate it 90 degrees around the origin. It's going to end up somewhere up here. So I'm going clockwise, and you rotate like 90 degrees. Now, I claim this can be written as an affine transformation. And the first key is figuring out what 90-degree rotation clockwise looks like in 2 dimensions. But this is not too hard to compute. Let's think about this example again. And let's think about 2 points. Let's think about 1, 0 and 0, 1. So we've got 1, 0 here. And we've got 0, 1 here. Okay. Well, we want to rotate everything 90 degrees clockwise. So 1, 0 is going to end up here at 0, negative 1. And this is going to end up here at 1, 0, right? And if you remember, I think homework like 2 or maybe 4, just from knowing where these 2 standard basis vectors go, I now know my linear transformation. And in fact, all I do is I say, where is 1, 0 going? Well, it's going to 0, negative 1. Where's 0, 1 going? Well, it's going to 1, 0. And so it turns out that this matrix here, this very nice looking matrix, if I do say so myself, is the matrix that rotates vectors in 2 dimensions 90 degrees clockwise. Which I want you to sit and appreciate how beautiful of a matrix this is, actually. Like, I know when I saw this the first time, I was kind of blown away. And I think it is genuinely awesome, actually, that, like, if you've ever, like, wondered why 90-degree rotation is so amazing, one way to explain it is that its matrix form is just beautiful. Right next to doing nothing, next to the matrix that means doing nothing, which is this matrix here, this is up there in the greatest, nicest matrices of all time. I want to point that out real quick. But anyway, so we now know what 90-degree rotation looks like. And what were the things I wanted to do? I want to take my point. I want to move it down 1 unit. And then I want to rotate it by 90 degrees. Oh, no, this is the wrong matrix. I just went on this whole speech about how it's such a beautiful matrix, and then I ruined it. That's how these things go. 1, -1, 0, right? And so, right, so I subtract, and because we're in parentheses, we do the parentheses first, so we move down first, then we rotate. And if we multiply this out, we'll actually get that this affine transformation, again, we have 90-degree rotation, and then we have our initial point. And then, if we multiply it out, this 0, 1 becomes a 1, 0. And so we end up subtracting 1, 0, right? So going down 1 unit and then rotating is the same thing as rotating and then going to the left by 1 unit, which kind of makes sense, right? Because we were going down, and if you rotate down by 90 degrees to the clockwise, you'll end up going left instead. Right, so we have, like, this notion of down, this down vector. If you rotate it 90 degrees up clockwise, then now we're going left. Right, so all we did is we just applied our rotation to our destination. And so let's call this transformation t, right? So we have t of x equals 0, 1, -1, 0 times xy minus 1, 0. Now, so what happens if I apply this to the origin? Right, so what happens if I apply this to 0, 0? Well, if I apply this to 0, 0, we're going to start at 0, obviously, and there's going to be nothing to transform because it's going to be 0, and so we'll just move to the left by 1 unit. So we'll end up somewhere here, right? Now, I'm going to draw this little arrow, right? Because we started at the origin, and then we moved left, right? And if I were a person, and I started at the origin and moved left, I would be facing this direction, right? So what if I apply t again, right? So I had, so that this first thing is t of x, or t of 0, 0, 2 actually. What about t squared of 0, 2? Well, we can do the math. We rotate this by 90 degrees. We rotate our point. I'm going to label this point 1. So we rotate our point 1 by 90 degrees. We'll end up at where that tick mark is. But then, again, we have to move 1 unit to the left. Right? So we'll end up somewhere there. I'm going to call this 2. But think about this. If I had been a person, and I already walked to 1 from 0. So I started at 0, I walked to 1. Getting to 2 is, for me, would just be rotating 90 degrees and then going forward, right? So I started out looking this direction, or not that direction, but the direction of that arrow that I was pointing to, right? I started out looking to the left, and I walked a degree, or a step. Now I turned to the right and walked forward another step. And like, you could do the math again, and if you want to get t cubed of O2, this is, well, you rotate this 90 degrees, so you'll end up where this white X is, and then you move left, right? And so that's going to end you there. And then if you do this one more time, you'll end up back in the origin, right? And so we have these arrows. We went in a big circle, right? And at the end, I'm facing here, right? And so if I wanted to do it again, I would turn 90 degrees to the right, I'd walk a unit. Turn 90 degrees to the right, walk a unit. Turn 90 degrees to the right, walk a unit, right? So, in some way, when I was, in some way, right, this point here, t applied to 0, 2, is kind of like saying I was at -1, 0, right? I was at point 1, but I was also looking to the left. And then t squared applied to 0, so applying t again is kind of like saying I'm at t2, but I'm looking up. And so this is kind of how I came to to what C-frames are, which is this. We're going to talk a lot more about this next week. This is actually going to be the final topic I talk about in the course, which is this matrix here represents rotation. Right, it represented a 90-degree rotation. And so all a C-frame is, the thing that you've been working with, is it's a 3-dimensional rotation plus a shift. Right? So we just talked about a 2-dimensional rotation plus a shift, but you can do 3-dimensional rotations plus a shift. Now, when I say the term rotation matrix for 2 dimensions, that's probably a lot easier to understand, right? We can either go some number of degrees clockwise, or we can go turn some number of degrees counterclockwise. But what does it mean to have a rotation in 3 dimensions? It's not quite as clear. So we'll talk a lot more about this next week, but I wanted to go a little bit into it, which is like, right, so like rotation in 2 dimensions can basically be boiled down to you pick some point, you pick some angle along sorry, there was a question in the chat. Yes, this is t applied 3 times to 0, and we end up here. Anyway, so like in 2 dimensions, rotation can basically be boiled down to we pick some point, some number of degrees, which is basically picking a point on the circle, and then we just rotate until we're there. If you try and do the same trick with a sphere, you'll very quickly fail, because if all you know is where you're on a sphere, think about it on a point on a sphere, right? You're on a point on a sphere right now. If you're in a spinny chair, I encourage you to spin around real quick, right? What you'll realize is you remained on the same point on the sphere, but where you were facing changed. Your rotation changed. So in 2 dimensions, the 2-dimensional rotation and 3-dimensional rotation are just kind of like fundamentally different beasts. And so we'll spend all of next week talking about three-dimensional rotations, and kind of what makes them so good, what defines a three-dimensional rotation, and finally go into some specifics about C-frames themselves. We'll basically only talk about three-dimensional rotation next week. We're not going to talk about any other dimensional rotations because three-dimensional rotation is incredibly useful, and also kind of the promise we made about this class. So I'm going to end a little bit early. So I'm going to end the recording, but I will stick around